Okay, we're picking up where we left off in the previous video, where we're going through this last section in chapter 8 of the trigonometry textbook on complex numbers. We're going to learn how to take powers and roots of complex numbers. Okay, but we talked about in the previous video where the radical comes into play, the radical symbol comes into play when it comes to roots of complex numbers. And so as we go through this section, I'll try and expand on this and point things out regarding to the radical symbol. So, okay, but first we're going to talk about the Moivre's theorem and powers of complex numbers. All right. So, powers of complex numbers and de Moivre's theorem. Because raising a number to a positive integer power is a repeated application of the product rule, it would seem likely that a theorem for finding powers of complex numbers exists. Yeah, so when it comes to finding powers of a complex number, we have a sense of how to do this. So if we were given a complex number, we want to find, so any complex number to the fourth power. And so when I say complex number, I'm referring to any number, even like a pure real number, like 12 plus 0i or whatever. Okay, if we wanted to find, so a plus bi to the fourth power, well, I mean, we have a sense of how to do this. We know how to multiply complex numbers, so you could just multiply a plus bi by itself, get a number, then multiply that by a plus bi, then multiply that result by a plus bi, right? Powers is just repeated multiplication of the same number. Okay, however, but what we learned regarding multiplication of complex numbers, the simplicity that comes out of using the polar form, we might be able to take advantage of that to come up with just a general formula or theorem for like any nth power of a complex number. So, and that is the case. We'll be able to do that. So if we change this 4 to just any nth power, okay. And so now from here, if we want to determine this, we could think about, we could convert this complex number to polar form, okay. And really, like even in practice, if you started with a complex number in rectangular form, that would be the most common case where you're working with complex numbers in rectangular form and you want to find some nth power of it. Well, what you would do is you would first convert it to polar form, okay? So that would be, you'd have r and then cosine theta plus I sine theta. Okay, and we know how to find the r and the theta. If we know this a and b here, well, this would be like x and y, you could think about, if we're thinking about this in terms of rectangular form. But a plus bi is the same thing, but I guess it's easier to see the rectangular versus the polar form with the x and y. Okay, but now this is to the nth power. Okay, so you agree that we haven't changed anything. Just writing x plus yi in the polar form, you have the same complex number z. We haven't changed anything. But we converted it to polar form because we know it's like really simple to interpret multiplication and even division in polar form, because all you're doing when you're multiplying two numbers in polar form, the radiuses, you're just multiplying them together. So if we're multiplying this complex number by itself n times, the resulting radius is going to be r to the n power. So the final radius is really simple. What about the angles? Well, we know when we multiply two complex numbers in polar form, you're just adding the corresponding angles. So if we're multiplying this complex number by itself n times, well, we know the final angle is just going to be that angle plus itself n times, which is just n theta. N times the angle. So plus I sine n theta, and that's it. There you go. That's the answer. So like all of these are equal. And now you can think about, though, that, so it's really easy, right? But you could think about, so like you start with a complex number in polar form. Let's say this is x1, or in rectangular form, right? You convert it to this, do the power, and then but then you convert it back. And now that's your final answer. Like what I'm trying to illustrate is that in a lot of ways, the polar form is just a tool you're using to perform an operation. Like the majority of the time, the most common case is you'll be working with complex numbers in rectangular form, but you might want to convert it to polar to do some operation. So then, but that's all of your work, all of your scratch paper. But in the end, what you've got is you started with this and you ended with this. You see, I mean, you could leave it in polar form if you want, but I think typically polar form is like something you do as an intermediate to doing a calculation. Okay, and so this is de Moivre's theorem. This is de Moivre's theorem where r cosine theta plus I sine theta, where that represents, that's a complex number in polar form to the n power is r to the n cosine n theta plus I sine n theta. And they just put that in the compact cis form here. Okay, so here's an example. They say find 1 plus I root 3 to the 8th power. Okay, so you could just multiply all this out using the binomial theorem or whatever. You could do that, but why not, do the de Moivre's theorem, convert this to polar form. So I'm not going to do that here. We know how to convert this to polar form. And what they get is, so 2 cosine 60 plus I sine 60, and that's all going to be to the 8th power. Okay, and now this is easy. You're going to have the result's going to be 2 to the 8th, and then 60 times 8 is 480. And that's it. 2 to the 8th is 256. Now, what they do, though, is when it comes to 480, what they do is they find the angle that's coterminal with 480 but between 0 and 360. Now, you don't have to do that. I mean, so if you've got the complex plane, the only reason you want to do that is because it's probably more presentable to represent a complex number with an angle that is between 0 and 360. That's more presentable. But I just want to stress, though, it's not like this is wrong at all. Because when you simplify this, like if you put this in rectangular form, let's say, you still have the exact same coordinates. If you use the angle 480 or 120, it's still the exact same coordinates in the complex plane anyway, right? But the only thing is if you put 480, it kind of makes it seem like there's two complex planes or something, and there's not. There's only one plane of complex numbers. And so when you go past 360, or you could use negative angles, it's almost kind of like, it makes it seem like there's more complex numbers. Once you go past 360, now you're in a new plane or something, and then that's not true. So it's probably more presentable, I would say, to keep the angle between 0 and 360 so the person can picture, okay, we'll easily see what quadrant it's in and have a sense of is it less than 45 degrees within that quadrant or great, is the reference angle greater than 45 or less than 45 in that quadrant? You can more clearly see that if you just put the angle as between 0 and 360. Okay, and then from there they convert this to rectangular form, which is cool, because then it's like you can put this final answer here. It goes from a rectangular complex number to the 8th to a new rectangular complex number. Okay, so that's powers of complex numbers. What about roots? All right, so now in regards to the idea of a principal root and a radical symbol, so in this section, in this textbook, they're not even talking about, they're not going to talk about principal roots, even though I wanted to talk about it because I think we're all familiar with what radicals are, and so there's natural confusion. But in this section here, just to point this out, in this section, as we go through roots of complex numbers, they're just referring to roots, not principal roots. And so when you say the root of a complex number or the root of any number. Like I could ask, what is, so 8. If I just kind of wrote an 8 here and I just said the square root of 8, that's all I said. Well, actually, let me change this to, let's do 49. I wrote the number 49 on a whiteboard somewhere, and I said square root of 49, the square root of 49. That's all I said. And I said, okay, do you have a response to that? Well, your response should be, you probably think about it for a second. You say the square root of 49. Well, in that case, you'd say, well, there's actually 2 square roots of 49. Because when you say the square root of something, you're asking what number, when you square it, do you get this number? That's what, when you say the square root of 49, you're saying, okay, what number, when you square it, do you get 49? Well, there's 2 numbers that when you square it, you get 49. Right? When you're asking for the nth root of something, if that's all you're saying, there's no, what I'm trying to emphasize is you're not saying principle. You're not using the word principle with the word root. You're just saying the word root. Then in that case, the question is, what number, when you square it, or when you take it to that n power, do you get this number? What number, or it could be numbers, whatever answers that question. That's what you're saying. It's only when you say the term, when you use the term principle, you're saying something different. And that's when the radical symbol comes into play. Remember, the radical symbol, it's not like the radical symbol is only a principal root for like even indexes or 2. No, the radical symbol for any index, no matter what the index is, 2, 3, 4, 5, this is always referring to principle. Always. A radical symbol is always referring to principle. And that's a different question. When it comes to a principal root, any nth root, there's only going to be one answer to that, one and only one answer. Okay, but just like talking about the nth roots of something, the nth root or roots of a number, it's just, you're asking, it's nothing to do with principle, nothing to do with radicals. Nothing to do with principle, nothing to do with radicals. You're just asking what numbers, when you take them to that n power, do you get this number? Okay, so like the nth roots of 49, we're saying what numbers, like a number A, when I take it to the nth power, do I get 49? Or what number, maybe there's more than one. But that does not mean we're saying this. No, that would be the principal nth root of 49. So there's no real, what's confusing about this is that there's no real like symbology for talking about the nth root of something. Like I can't, okay, this is the principal nth root of 49. There's no other like nice clear symbol I can put to talk about the general question of what numbers, when you take them to the n power, do you get 49? It's just kind of like a question. Nth root or roots, could be root or roots of 49. That's really it, okay? So that's how we're in this section, we're talking about roots of complex numbers. That's the perspective. This section is saying nothing about principal roots of complex numbers, even though I'm going to touch on that a little bit. This section is not saying anything about the idea of a principal root of a complex number. We're talking about here that we've got any complex number in the complex plane. Any complex number, it could be pure real, 8 plus 0i, pure real, whatever. We're asking, okay, if we're the nth root of this, 8 plus 0i, or minus 2 plus 3i, or 5i, the nth root of, or roots of any of these numbers, we're trying to answer the question, what are all of the numbers in the complex plane that when you take them to the n power, are you going to get this, or this, or this? That's what we're answering here in this section. And that's it. The idea of a principal root, we talk about more in complex analysis, but I'm going to touch on that here. Okay. So the first thing to note is that, so they start by saying, so roots of complex numbers, it says every non-zero complex number has exactly n distinct complex nth roots. And this is a really important sentence because it's easy to forget that, like, we tend to think that the number 8, okay, this has only one cube root. And in actuality, what this is saying, it says every non-zero complex number. So that's any number in all of mathematics except for 0. 8 is a complex number, right? Of course. They're saying 8. So across the board, the number 8, or 8 plus 0i, is going to have exactly indistinct complex nth roots. So like, okay, so the what are the cube roots of 8? Well, one of those is going to be 2, but that's still complex. It's 2 plus 0i. Okay, 2 cubed is equal to 8. But the other ones, you know, we would typically think, well, 8 is the only root of, or 2 is the only cube root of 8. Well, no, it's not. And so, but what that means is that what we're confused about is that the other ones are going to be, you know, A1 plus B1i. They're going to have an imaginary part. But still, if you cubed these, you're going to, and like with the Moivre's theorem, you're going to get 8 plus 0i. And so that's a general rule that the nth root of any number in all the complex plane is going to have exactly distinct roots. Okay? And another reason it's confusing is because it's like, well, wait a minute, like why is this getting more complicated? If I took the principal cube root of 8, I get 2. If I took the principal cube root of minus 8, I get minus 2. But then even outside of the principal cube root, even across the board in general, the only number when you cube it, you get 8 is 2, and the only number when you cube it, you get minus 8 is minus 2. There was no confusion here before. Like, why is this? We invented complex numbers. Why is this getting more complicated? There was no problem here. Like we were completely fine when it came to odd roots of positive and negative numbers. Like even for that matter, that means that what this theorem is saying is that so we have the principal fourth root of 16 we know is 2, but we also know that minus 2 to the fourth is 16. But this is saying that all of the fourth roots of 16, there's going to be just 16, positive 16. There's going to be 4 of them now. And that's correct, according to this theorem. So why are things now more complicated than they were before after inventing complex numbers? What's going on? Well, no, like the idea is that we invented the complex numbers, and they've successfully allowed us to answer questions regarding any kind of even roots of negative numbers, or like we now have numbers that when you take them to even powers, you can get like negative numbers. And so it's answered those questions successfully, but you can't just invent these new numbers and ignore all of their additional effects. Like you can think of like the fact that we've got 4 roots of positive 16 now instead of just 2. That's just a side effect of inventing complex numbers. You have to take it all, everything that comes with the invention. You have to take everything that comes with it, and so that's where this is coming from. So we accept the fact that, okay, there's going to be, in general, across all numbers that exist, there's going to be 3 of them instead of just 1, that when you cube it, you get 8. But we're okay with that because these new numbers are what they've given us for dealing with these even roots of negative numbers. We're okay with that trade-off. So that's the idea of the more advanced complex analysis course that I'm going to be posting later. Is that you need to study complex numbers across the board and see and like integrate them with all of the existing mathematics. Like you're not just going to study the how complex numbers are related to even roots and just ignore everything else. No, you want to understand complex numbers as well as you understood real numbers before you made complex numbers. You want to become comfortable with complex numbers across all of mathematics, graphing, logarithms, everything. Even though their only real purpose was involving even roots of negative numbers. Okay, so now, but again, so right now all we're talking about is just what are all the nth roots of any number, any complex number. Okay, we're going to use the Moivre's theorem to answer this question. So, okay, the idea is what is an nth root? So for a positive integer n, now, why are they saying n is, I don't know if we think about first roots, but I guess you can do that. So yeah, okay, for a positive integer n, the complex number a plus bi is an nth root of the complex number x plus yi if the following holds. So they're just stating the idea of what a root is from a complex number standpoint. We know that if we have the number 16, okay, that there's 2 square roots of 16, not principal. We're saying what are all the square roots of 16? There's 2 of them. But how do we know that? How do we know that these are 2 square roots of oh no, there's 4. How do we know that these are 2 square roots of 16? Because we know when you square these 2 numbers, you get 16. And so from the complex number standpoint, all they're saying here is that if you have a complex number, x plus yi, okay, an nth root of this is going to be any number that when you take it to that n power, you get this. So they write it like this. That's it. That's what an nth root means. But there's obviously there could be multiple of these. You know, we had 16. There was 2 of these scenarios. 4 squared was equal to 16. There was one root, 4, and there was another root. But that's the idea of a root of a complex number. But again, just to stress that even 16 is included as a complex number. So, okay. Now it says positive integer n, so that would include 1. So I guess that's like saying that it's kind of confusing because it's kind of like, to me, that's if you're including 1, it's like saying that, well, then 16 is a first root of 1. I guess it is. So what are all the first roots of 16? Well, it's only 16. That's kind of confusing. So we typically don't, like when it comes to radicals, the principal nth root of something, the definition of a radical, you don't include n is equal to 1. It's n is any positive integer greater than 1. So, but all right. So that's the meaning of a root of a complex number, x plus yi. So now they go through an example here. It says, let's find the 3. We know there's going to be 3 complex cube roots of this complex number, right? If we want to find all of the cube roots, which we know is going to be 3, how can we find all the cube roots of this complex number? All right, so it says, so for example, we're looking for a complex number, r cosine alpha plus I sine alpha, that will, we're assuming this is one of the cube roots. There's going to be 3 of these. And this is one of them. And it's this form r cosine alpha plus I sine alpha. And so since this is one of the cube roots, the idea is when you cube this, you're going to get this. And so that's what they write here. Okay? So then they simplify this using de Moivre's theorem. So this becomes r cubed, and then the alpha times 3 is equal to this. Okay? Now, then they match up terms. So one thing we can see is that r cubed is going to be equal to 8. So what does that mean r must be? R is one of the, remember, r is part of one of the roots. That's the form of a root. One of the cube roots of this complex number is, the radius is r and the angle is alpha. Okay, so what does that mean? What does this mean, this force r to be for the one or all of the roots? Well, this means that r is going to be equal to 2. And this is going to be, r has to be 2 for all 3 of the roots. Has to be. Okay, now you might be a little bit confused here because it's like, okay, so I guess we took the cube root of both sides of this to solve this. I guess we kind of did this. Okay, so, but, okay, there's that radical again. Well, this is not so bad. There's only one principal cube root of 8 is 2. But then, all right, what if we were doing square roots or fourth roots and we had r to the 4th is equal to some number? You know, it could be anything like 16. Or, okay, well, let's say square roots to keep it simple. Let's say we had a square, we were finding the 2 square roots and we had r squared is equal to 16, but then r would be plus or minus 4. But then even more than that, didn't we just say that there's 3? We introduced the cube root here. So isn't there 3 numbers that, like we've been talking about, there's 3 numbers that when you cube them, you get 8? Well, no, okay. When it comes to that, remember that this is part of the definition of the polar form of a complex number, okay? When it comes to the definition of the polar form of a complex number, okay, the R here is any real number. Okay, with the R, we're only talking about real numbers. You can't have a complex number. It's part of the definition of the complex number. It's kind of like there's no A plus BI. A and B are real numbers, right? Okay, so that's the first thing. So that eliminates writing out, all of the complex roots of this, of 8 here. No. Now, but what about the plus, this case where you could have like plus or minus potentially? Well, remember also the polar form of a complex number, R is positive. R is positive. I mean, like you technically could make it negative, and you could still map out a number in the complex plane. But like in general, R, the standard form is R is always positive. So even if you've got like a square root or an even root case, like we could have done this. So R to the fourth is equal to 16. So, well, there's two numbers that when you take them to the fourth power, you get positive 16 plus and minus 2. But it wouldn't matter anyway because the original R here is going to be positive. So you're going to choose the positive no matter what. Okay, so with that then, what we're going to be able to write is that if you're finding the nth root of any complex number, then you take the R on the the R. So okay, you're finding the nth root of. Yeah, this is also kind of confusing. You're finding the nth root of this complex number. The nth root. Then all of the n roots are going to have the same radius, with that radius being the principal nth root of R. And you can put a radical in here. So the principal, we know what the principal nth root, the radical, is, it's always going to return a positive number. So that makes sense. So by putting this nth root radical here, the principal nth root is a radical, that covers all possible cases that will get exactly what we need. Okay, and I'm saying principal nth root radical because as I talked about in the previous video, there are principal roots of complex numbers, and that can create confusion, but we don't think about the radical. When we're thinking about the radical symbol and the principal nth root in terms of what the radical symbol, we're thinking about from the perspective of all real numbers, of how we learned it in pre-algebra. That's how we're thinking about it, except for that the one caveat that, like, yes, we do allow for this. We can bring imaginary in, but other than that, we're thinking about this from the perspective of like R is a real number, not a complex number, and the output of this, the output of R to the n, is always some real number. So this would be, let's see, it's always some real number, except for this one special case on the side where that doesn't happen. Okay, so, and you'll see why I keep saying, even though there are principal roots of complex numbers we're not going to mix that. We're not going to be putting any complex numbers inside of radicals, because it's like the principal root when it comes to a radical symbol is going to, you look at that differently, which I realize this is all confusing. So just try and do the best you can to go with it, but we'll learn more about this in the complex analysis course. So, all right, now. So that means for this problem that we're working on, each of the radiuses of the three roots is going to be 2, because the principal cube root of 8 is 2. Okay, so that's great. So we matched up the R cubed and the 8. Now let's match up other terms. Okay, so we can match up the fact that we see that cosine of 3 alpha is equal to cosine of 135 degrees. And sine of 3 alpha is equal to sine of 135 degrees. Okay, so now remember, we're trying to solve for alpha. if we come back here, this is the form of the root of the three roots. We're trying to solve for r and alpha. And since we know the r is going to be the same for each of the three roots, well, that must mean that the alphas are going to be different, because we know that we're going to have three distinct roots. So we're trying to solve for alpha. So to do that, we know how to solve something like this. So we take the inverse cosine of both sides, and also we take the inverse sine of both sides here. And the way you can think about this is that this is like an and criteria. We're looking for alphas that satisfy this and this. Now, what's going to come out of both of these is the same equation. 3 alpha is equal to 135 degrees. Okay, and so we're only going to write this once. But if the argument was different here and the angle was different here, then we'd have to kind of like write out both, and then we'd be solving both the equations at the same time. We're still solving kind of two equations at the same time here. But we're not done yet, though, because this is not just 135. We introduced an inverse function, an inverse trig function. So we're really asking, so it was inverse cosine of cosine 135. What you're asking there is, so cosine 135 and sine 135 aren't angles. That's why they go their inputs into the inverse function. And so, but the question that's being asked is, overall, the inverse cosine of the cosine of 135. What you're asking there is let's see, cosine of 135 is minus root 2 over 2, and sine of 135 is root 2 over 2. Oh no, this is minus. Okay, so what you're asking is, here, what angle, when you take its cosine, do you get minus root 2 over 2? That's what you're asking. Here you're asking, what angle, when you take its sine, do you get root 2 over 2? So, when we introduced an inverse cosine to solve for 3 alpha here, we would list out, the way we did it was, we would list out, most of the time there was 2 angles between 0 and 360 that answered that question. And then we would say those 2 angles, and then every angle coterminal with either of those 2 angles is true for the question of what angles, when you take their cosine, do you get minus root 2 over 2. Okay, but we have an and here. It needs to, what we're really saying is, since it needs to satisfy both these at the same time, we're saying what angle, the angles we want to list here are, what angles, when you take their cosine, do you get minus root 2 over 2? And at the same time, when you take the sine of that angle, you get root 2 over 2. It's both of those. It's both of those. Okay? And so what's going to happen in that case is there's actually going to be only one angle, if you think about it. There's only going to be one angle between 0 and 360 that answers both of those questions at the same time, and that's going to be 135. And so, but then from there, obviously, any angle coterminal with 135 is also going to answer that question. So we put plus 360 times some positive or negative integer k. But we would put, if this was in radians, we'd put 2 pi. And now this is correct. Taking the inverse cosine sine and getting 3 alpha is equal to some angle. This is correct. We couldn't just put 135. That wouldn't be solving the equation, right? This is correct. Okay, now we can move on. So let's divide both sides by 3. Okay, so there we go. Now we solve for alpha. But we've got an infinite number of alphas because k can be any integer, right? So what do? Well, it's like when we're solving any trig equation, you get an infinite number of answers, but then you look at your specific problem and see, okay, can I eliminate some of these answers? And yeah, we can do that here because we're looking for numbers in the complex plane. That when unique numbers in the complex plane, that when you cube them, you're going to get this 8 times 8 cis 135 degrees. Okay, we're looking for these unique numbers. Well, there's no need to state a number that's like two complex numbers with like the same complex number twice. And we'd be doing that if we used like coterminal angles. So the way you look at it is, when you're talking about the complex plane, the way the default way to look at it is you want to specify angles between 0 and 360, and then don't include angles that are greater than 360 or negative, even though mathematically that's completely valid. But if you're just looking to, like, identify all the complex numbers in a plane, then you kind of look at it like, okay, you're giving an angle between 0 and 360. So with that, we can choose k values, that only the k values that are going to specify some angle between 0 and 360, and just ignore all the other ones. That's what we're going to do. And so what we find is that to do this, all we need to do is say, so here we're going to choose k is equal to 0. In that case, we'll have 135 divided by 3. That's going to be 45 degrees. Perfect. So that's going to be one of the complex numbers is going to be r cis 45 degrees. So r is going to be 2. Perfect. If we choose k is equal to 1, we're going to get some other angle between 0 and 360. If we choose, or including 0 or 3, no, but greater than or equal to 0, less than 360. If we choose 2, we're going to get another angle between 0 and 360. And then if we chose 3, that's going to be redundant. 3 would get an angle greater than 360. We don't need that angle. And if we chose -1, we'd get a negative angle. We don't need that either. So we can stop here. And so there you go. That's what they do. K is equal to 0, 1, and 2. You get 45, 165, 285. We know the radius is the same for each one of those angles. And so that's going to be your 3 complex numbers. That when you cube them, you get this 8 cosine 135 plus I sine 135. And that's what they do. They list them out here. There they are. That's the 3 cube roots of this 8 cosine 135 plus I sine 135. And this process that we just went through, you can do this with any complex number, and you can get the in roots. We could do this exact same process with the 4th roots of 16. There's going to be 4 of them, right? Not just 2 and -2. So the 4th roots of positive 16, I'm not putting a radical, okay? The 4th roots of positive 16, since it's 16 is a complex number, right? All numbers are complex numbers. There's going to be 4 distinct roots, 100%. Now, 2 of those are going to be, so, okay, the 4th roots of 16 plus 0i, 1 is going to be 4th roots. 1 is going to be 2 plus 0i. And another one is going to be 2 plus 0i. Okay, and you would find that if you go through this process we just did, that's what you're going to find. But there's going to be 2 more that are obviously going to have imaginary parts. But still, when you cube them using de Moivre's theorem, you're going to get just 16 plus 0i. That's the idea. Okay? So, now, from what we just did, can we come up with a general formula for what are the nth roots of any complex number z? So you have a complex number z. What are the nth roots? Well, what I mean by that is, so like we can say that the nth roots, all the radiuses are the same, and they're going to be given by the nth root of r, where r would be okay, we have a complex number that we could put in polar form, r cis theta. The roots are going to all have radius the principal nth root of r, okay? And then the angles are just going to be, let's see, the angles are just going to be, from what we just did, we can see that the angles are going to be, so the angles alpha are going to be, you take the angle of the complex number you're trying to find the roots of, and you say, okay, theta, you just write that angle, and then it's going to be plus either 2 pi or 360 times some positive or negative integer k, and then it's going to be divided by n, right? We divided by 3 here, But if you think about the process we went through, what would always happen is you're dividing by n, whatever the nth root you're trying to find, okay? But then the k, you're not going to have an infinite number of alpha values. There are only going to be certain k's you're going to choose. And what it's going to be is, the k is going to be 0, 1, 2. Just keep counting up all the way, and you stop at n minus 1. Meaning that, so we stopped at k is equal to 2, even though our n was 3, because we're just trying to get 3 numbers for 3 roots. But one of the numbers is 0, so you stop at n minus 1. And that's the general idea. That's kind of if we come to the next page, that's the nth root theorem. If you want to find all of the roots, the nth roots of any complex number, well, then you put it in polar form, and in polar form, r is going to be positive, and theta could be in degrees or it could be in radians. So there's it in polar form. You want to find the all n roots of this, okay? Well, then the final result, the roots are going to be the following. The radiuses are going to be the principal nth root of r. That's going to be all the radiuses. And then they're all going to have they have to have different alphas, where the alphas are given by, and they write out what we just wrote out. Here it's in degrees, here it's in radians. Okay? Now, what we're going to learn in the complex analysis course is that in actuality, any complex number, no matter what it is, does have a principal nth root. It does have a principal nth root, and it's really simple. It's really easy to get what the principal nth root is. It's just the root that corresponds to the k being equal to 0. That's it. And so, at first, the first thing you can probably think about when you hear this is that, well, that's great. So we can just stick, 3 minus 2i inside of the principal root radical symbol. Okay, what's the third principal root of 3 minus 2i? You go off to the side, you do the whole roots analysis, and just find that k is equal to 0. The complex number corresponding to k is equal to 0. Maybe it's real, maybe it's pure real, maybe it's pure imaginary, maybe whatever. It could be like 5 plus 2i, and there you go. Well, unfortunately, it doesn't work out this way. You really want to stick with, when you see a radical symbol, you're thinking about the principal roots from the standpoint of where you're dealing with all real numbers. The inputs are real numbers, the outputs are real numbers, except for the one caveat where you have a principal square root, this one caveat. Okay, it has to be a square root. In this case, the input is still a pure real number from the real number line, but you can take out an I. But other than that, radicals, you're thinking about real numbers. And the reason why, just to give you a preview on this, the reason why is because it actually does, a lot of the time it does work out if you have if you had this, and then you came off to the side and found all 3 of the cube roots of the complex number 8 plus 0i, well, the first cube root, the one that corresponds to k is equal to 0, is going to be 2 plus 0i. Perfect. Great. But the problem is it doesn't always work out this way. So, like, for example, if you did the principal cube root of minus 8, if you're thinking about this in terms of the real number domain, real numbers, this is minus 2. However, if you came off to the side and found all of the cube roots of the complex number minus 8 plus 0i, then the one corresponding to k is equal to 1 is going to be minus 2 plus 0i. And so if you actually found from a complex analysis standpoint, what is the principal cube root of minus 8? It's actually I think it's 1 plus I root 3. And so that's where it gets confusing. It's weird to think about. It's like, well, okay, so are these different numbers? Well, no, of course not. Of course not. In true reality, every number is a complex number. Absolutely. No, this even inside the radical, technically, this is minus 8 plus 0i. Okay, but which one's the actual principal root, minus 2 or 1 plus I root 3? That's something we'll get into later. Okay, just for now, don't mix when you're working with radical symbols and the term principal root from the perspective of a radical symbol. You're thinking about that from the real number domain. 99% of the time working with real numbers. Okay, so now this next example, it says find the 2 square roots of 4i. So yeah, let's work an example here. So we've got the complex number 4i, and we want to find its 2 square roots. And so yeah, notice that it's not, for all these examples, we're never going to be putting radical symbols in here. It's always just, the only way you can state this is that what are the square roots of 4i? You kind of have to state it as a question. That's the only way to talk about the roots of a number, is like in the form of a question. If you're looking at that big picture, or you're not talking about principal roots. So, okay. So what we do is we want to put this in polar form. So this is, the radius is going to be 4, and the angle, we know this is going to be 90. Okay, so now let's see, I'm going to just write it as x1 and x2 are the 2 complex numbers that are the square roots of 4i. So, okay, the radiuses are going to be the principal square root of 4. That's going to be the 2 radiuses. So each of these are going to have radius 2. Okay, and then let's see. What are the angles going to be? Well, okay, we do that. There's going to be 2 different alphas. Alpha is, and we put the angle of the number we're trying to find the roots of, plus 360 times some integer k over, in this case, it's going to be 2. And then we just, the 2 angles are going to be k corresponding to 0 and 1. All right, great. So k is equal to 0. 90 divided by 2, that's 45. Okay, k is equal to 1. Let's see, 360 plus 90 is 450. 450 divided by 2 is going to be, or no, it'd be 2. $225. And that's it. There are the 2 roots. And they actually did this in radians. So pi over 4 is 45. 5 pi over 4 is 225. And yeah, but they convert these back to rectangular form. And there's these 2 numbers in rectangular form. So if you squared either of these 2 complex numbers, you're going to get 4i. Okay, but now, according to complex analysis, the principal root, or the principal square root of 4i would be this. I believe that should be this. Okay, now in this next example, we're going to see that there's actually a trick we can use to understand roots a little bit better and to actually make solving for them quicker. All right, so it says find all of the 4th roots of this complex number, and then write them in rectangular form. So they first convert this to polar form. I'm not going to do that again here. Polar form is 16 cis 120. So 16. All right. So we know all 4 of the roots are going to have radius, the principal 4th root of 16, right, which is 2. So they're all going to have radius 2. Okay, now the angle is going to be, for each of these, is going to be, so it's going to be alpha is equal to, we take 120 plus 360 times k divided by 4. And then with k being equal to, we go 0, 1, 2, 3. So they plug in all of these k's and they get, if we come here, alpha is equal to 30, 120, 210, 300. And so there you go. There's 2 cis 30, 2 cis 120, 2 cis 210, 2 cis 300. They convert each of those to rectangular form, and there are the 4 roots. If you take any of these to the 4th power, you're going to get that minus 8 plus 8i root 3. So, but now what they do is they say, let's graph these in the complex plane. And one thing you can think that's going to be interesting about graphing these is that they're going to all be contained on a circle of radius 2, a circle in the complex plane of radius 2, right? Which makes sense because the roots of any number are all going to have the same radius. So they're in the complex plane. They've got this circle of radius 2, and then there's the different angles, and they plot them. And what you can notice here is that the angle between each of these complex numbers is all exactly the same. And that's actually going to be the case, always going to be the case with roots of complex numbers. They're angled. They're going to be on the same circle, and they're all going to be equally spaced in terms of angle. And so with that, you can think about, we could have gotten to, if we come here, we could have gotten to, so we found the first angle, 30, k is equal to 0. Then we could have found the second angle was 120. And now if we see that, okay, so 30, to get to 120, you added 90. So we know they're spaced 90 apart, so we didn't actually have to plug in k is equal to 2 or 3. We could have just added 90 to 120 and then 90 to 210 to get the other angles. Okay, but actually, if you think about it, we could have actually made it even simpler than that, because they're spaced all the way around 300, the full rotation. So they're equally spaced around the full circle. Well, the full circle is always 360 degrees, number one. But number two is, we know there's always n roots. For the nth root of a number, there's going to be n roots. So in other words, we could have figured out that, okay, since we're finding the fourth roots of some complex number, that means there's going to be 4 roots. Well, if those 4 roots are going to be equally spaced around 360, we'll just take 360 divided by 4, which is 90. So we know they're going to be spaced 90 degrees apart. So with that, we could have just said, okay, we found the first angle is 30, and then we know they're spaced 90 apart, so just keep adding 90. So you can find that first angle, corresponding to the principal angle, corresponding to k is equal to 0, and then just added 90 from there. Each of these is going to be 90. If the fourth roots of something are going to be spaced 90, the third root's going to be spaced 120, etc. Okay, in this last example, it says to find all of the complex number solutions to the equation x to the 5th minus 1 is equal to 0. And so, yeah, this is what I was talking about in the previous video, the introduction to this section video, and that, so you're going to, if we want to solve this, x to the 5th is equal to 1, we'd add 1 to both sides. Well, we would typically think to take put a radical, a 5th root radical on both sides, and you get x, is equal to this, right? But the way you want to think about this is that it's just like with the inverse trig functions. When you introduce an inverse trig function to solve an equation, you're really not using the actual inverse trig function. And so from that sense, we're not really thinking about this as what is the principal 5th root of 1. It's really more of a question of what are all of the numbers that when you take them to the 5th power, do you get just 1? So, yeah, this could be confusing because it's like, well, in that case, we're thinking about 1 as a complex number. We're going to have these complex solutions. So are we mixing in complex numbers with radicals? No, because this is more of like a symbology here. When you have, in the same way that using an inverse trig function to solve an equation is like a symbology. When you have it this, okay, what you're asking is, if you want to solve for x, you're asking what are all the numbers that when you take them to the 5th power do you get 1? That's what you're asking. You really don't even have to put a radical symbol on both sides. Okay, and so that's what they do. They come off to the side and find all of the 5th roots of the complex number 1 plus 0i. Now, just to point out though, if you're not allowing for solutions that have imaginary components in it, so if you're solving something and the question is saying, okay, but there's no imaginary numbers. If there's an imaginary solution, then just say no solution instead of actually listing the number. Well, in that case, then if you had x to the 5th is equal to 1, well, you could just introduce the radical. And if you've got a odd index, well, we know there's only going to be, you can just evaluate the principal root. And just as it is. If there's an even index, then put the plus, or you can use that plus or minus, that square root property, even with a even with an even index that's not 2. And it'll work there. Because like with 16, there's 2 numbers that when you take them to the 4th power, you get positive 16. 2 and minus 2. And then if there's a negative number inside of an even index radical, well, then there's no solution. So yeah, you can, in that case, you can apply the square root property to even any radical that has an even index greater than 2, just put the plus or minus. And then if there's a negative number under an even index radical, then you just, there's no solution. So here we would, in that context, we would say if we had x squared is equal to minus 1, we'd say no solution. Or x to the 4th is equal to minus 12, no solution. Okay, so let's see. Here they find the 3 numbers and plot them so you can see they're all spaced 72 degrees apart. All of the 5th roots of 1 that satisfy the equation x to the 5th minus 1 is equal to 0.